Okay, here we go. 4.1, max minimum values, part 2, equivalent to 4.3 homework in your XYZ homework. The next thing we're going to talk about in this section is called the extreme value theorem. Anytime anything has a name, it's typically important. So you want to write this one down into your calculus notes. When we do use it, I will abbreviate it EVT. If we have a continuous function on a closed interval, then the function will always attain a maximum value and it will always attain a minimum value. Always. As long as these hypotheses are satisfied. The function has to be continuous and it has to be defined on a closed interval. So that means it has to be defined at both endpoints and for every point in between. So all extreme values for a function defined on a closed interval will happen at either an endpoint or at a critical number. So let's write this down. So extreme value theorem. And then we're going to write down all extreme values extreme values are your absolute, or otherwise known as global, max and mins. For a function defined on a closed interval will happen at either an endpoint or a critical number. Today, finding absolute max and mins for a continuous function defined on a closed interval. The process is called closed interval method. For finding absolute or global extreme values. Okay, we're going to do process by example. Find all extreme values for f of x equals 2x squared minus 3x plus 1 on, let's do -1 to 3. Because this is a continuous function, we know that all polynomials are continuous, and it's on a closed interval, we are guaranteed that this function will have an absolute maximum and an absolute minimum. So, step 1. For any function, this would be the process. Find the critical numbers. So we take the derivative, set it equal to 0. So 3/4 is a critical number. And then we also determine where this function's undefined, and seeing its derivative is linear, it's defined everywhere. So therefore, the only critical number is 3/4. So step 2, now remember, extreme values happen at either critical numbers or endpoints. So we have to check both endpoints and all critical numbers, in this case, just one. So we literally just make a table of values, create a table of values inputs are going to be the endpoints of your interval and all critical numbers. We don't always just have one. So we're going to make table of values. My inputs are critical numbers and my endpoints. So my endpoints are -1 and 3, and that's from up here, the endpoints of my interval, -1 and 3. So those are going to be my first set of inputs. And then list all my critical numbers. And the only critical number here is 3/4. And then we're going to stick them into the given function. Remember, the given function was 2x squared minus 3x plus 1. So if we stick -1 in here, we get 2 plus 3 plus 1. If I do this correctly, that's 2 plus 3 is 5, plus 1 would be 6. At 3, the output would be 18 minus 9. 9 plus 1 would be 10. And then previously, in our first part of this lecture, we calculated this to be -1/8. If you find a mistake in my algebra, please, by all means, send me an email, and I will be happy to correct it and send an email out to the class. So here, critical number 3/4, endpoints is -1/3. So step 3 is to identify from this table simply the largest output, the one that's highest up on the y-axis, and the lowest output, the one that's lowest on the y-axis. And identify the largest and smallest outputs. So here, the largest output would be 10, and the smallest output would be -1/8. So therefore, that's our answers. This function, f of x equals 2x squared minus 3x plus 1, has an absolute maximum at the endpoint 3, and the maximum value is 10. It has an absolute minimum at the critical number 3/4, and the absolute minimum value is, the absolute minimum value is -1/8. So therefore, f of x has an absolute maximum value of 10. It occurs at the endpoint x equals 3. And it has an absolute minimum value of -1/8, which occurs at the critical point, which happens to be the vertex of this parabola, -3/4. If we graph this function again, I graphed it previously, it looked like this. So we're only looking at it between -1 and 3. So we can see if we look at this function between -1 and 3, and only look at it from here to here, because we don't care what happens beyond those points, it reaches its highest value at 3, the output is 10, and it reaches its lowest value right here at the vertex at 3/4, and that output was -1/8. All right, let's do one where the critical numbers are not as nice and obvious as we have in a quadratic. How am I doing on time? All right, I think we can do it. Let's go. All right, so let's find the absolute max and min values of f of x equals the cube root of x squared minus x on, let's do, I'm trying to save myself a little time here. Let's do 0 to 2. All right, so not as straightforward. We can graph this and see that it has kind of a funky shape. So first thing we do is find the critical numbers. I'm going to rewrite this function. All right, all radicals as power functions, so then it's easier to take the derivative. So now I'm going to use the chain rule in combination with the power rule. Bring the power out front, leave what's inside alone, drop the power by 1, multiply by the derivative of what's inside. Right now, this is going to get a little bit trickier to work with. I'm going to rewrite this, putting the x squared minus x to the negative 2/3 in the denominator. All right, you might look at this and be like, oh goodness, how am I ever going to determine where this equals 0 or it's undefined? Well, anytime you have a fraction as a derivative, remember that a fraction equals 0 only when the numerator equals 0 and a fraction. So in this case, we can get our first critical number by setting the numerator equal to 0. And we get x equals 1/2 as our first critical number. A fraction is undefined when the denominator equals 0. Because our critical numbers are when a fraction equals, when a derivative equals 0 or is undefined. So a fraction equals, this happens to be a fraction. The fraction equals 0 when the numerator is 0, and that happens in this problem when x is equal to 1/2. A fraction is undefined when the denominator equals 0. So now we can solve for that one. So we take the denominator and set it equal to 0. This is not nearly as horrible, because in order to solve this, I could divide the 3 out on both sides. So I'm really just solving x squared minus x to the 2/3 equals 0. Then I can raise both sides to the 3/2 power and get rid of the radical in the power. So really, the denominator, 3 times x squared minus x to the 2/3 power, only equals 0 when this stuff inside the parentheses equals 0. Now I can factor out the x. So then we get x is equal to 0 and 1 are my other critical numbers. So therefore we have 3 critical numbers. X is equal to 1/2, 0, and 1. So now if we follow the process, we make a table of values. Remember, the original function is the cube root of x squared minus x, and we're looking at this on 0 to 2. So a critical number just happens to be an endpoint, and that can happen. So we can make a table of values. My inputs are going to be my endpoints, 0 and 2, and then my critical numbers, 1/2. I don't need 0 again, and 1. So now I have to plug all these values into the function and get the outputs. If I plug in 0 in, I get the cube root of 0, which is 0. If I plug 2 in, 4 minus 2 is 2. It's the cube root of 2. So let's use exact values. If I put in 1/2, 1/2 squared minus 1/2 would be negative 1/4. So this is the cube root of negative 1/4. And I'm just going to leave it like that for now. And then if I put 1 in, I get 0 again. So always, anytime you have a function that's continuous on a closed interval, cube roots are continuous everywhere, closed interval 0 to 2, you will always have an absolute maximum and an absolute minimum. Absolute maximums happen at either critical numbers or at endpoints. And it's okay that sometimes your critical numbers are your endpoints. So what we do is we find the largest value of these. I don't know exactly what this value is, but I know it's less than 0. I don't know the exact value here. It's not a nice number, but I know it's greater than 0. So this is the largest output. And this is the smallest, or the one lowest on the y-axis. So this is my smallest output. So therefore, I can conclude. So this is not as nice or as easy as a polynomial. Therefore, f of x has an absolute max value of the cube root of 2, and it occurs at x equals 2. So the input 2 gives me the largest output on this interval. If the question asks for the value, make sure you give the output. If it asks where it occurs, it's looking for the input. And then we conclude f of x has an absolute minimum value. The value would be the cube root of -1/4. And yes, you can take cube roots of negative numbers, not square roots of negative numbers. And it occurs at x equals 1/2. Right, so that should get you started. Be sure to remember to watch the videos associated with the questions. Make sure you're reading these sections in the textbook too. You have to work hard on your end. The to-do for this section. Please read 4.1 in the text. The exercises that are great practice are 1 to 13 odd, 29 to 43 odd. So this is in your text. 47 to 61. Perhaps do every other odd. Lots of problems here. 65, 69, and 73. And I know this is a lot, especially now with the XYZ homework. That's replacing your quizzes. So let's do the XYZ homework. 4.3. And XYZ homework 4.3 is due on 4/3. So next Friday. So you can watch this lecture, you can read in the book, and then you can go do the 4.3 homework. It's due next Friday. So any lectures I post on Monday and Wednesday, the homework for those sections are due the following Friday. There you go. Have fun.